Okay, let's talk about energy and the work-energy theorem. The work-energy theorem is much more important than the other lot of waffle that came before this. This is where you should focus more attention, is on the work-energy theorem. Okay, so in grade 10 we learned about potential energy and kinetic energy. So by definition, potential energy is the energy of an object due to its position in a field, and in this case a gravitational field. Remember when we do electrostatics, there's a definition that's very similar to this, that objects can have forces and energy based on where they are in the electrostatic field. And when we're going to go on and do electricity, there's a magnetic field, and we can make things move in a magnetic field because they've got some energy, they've got some potential energy due to that. So to think about the gravitational field, here's the Earth. The Earth is full of particles, it has a large mass, and according to Newton's laws, okay, of universal gravitation, when the ball is just above the surface of the Earth, it's got a small amount of potential energy, because realize the gravity is going to pull it back down to the Earth. But if you make it move really high above the Earth, it gets more gravitational potential energy the further it's from the Earth. Because think about it, if you drop this ball on your toe from like 5 centimeters above the ground, and you drop this ball on your toe from 5 kilometers up in the air, then which one is it going to hurt your toe more? Obviously this one, because it had a lot more potential energy when it was high than when it was low. So potential energy is the energy of an object due to its position in a field, and in this case the gravitational field. So potential energy is the weight, because this is the force that you're going to oppose due to gravity, times the height. We measure it in joules, so mgh. Okay, so here the mass m, the height h. Kinetic energy is the energy of an object due to its motion. Okay, so now there's a whole lovely proof here, which I'm not going to go into, that proves that kinetic energy is equal to the force times the displacement. Okay, so we're going to be relating kinetic energy. Remember, we always have a half mv squared for kinetic energy. We are relating work now. Kinetic energy, we are relating it to work, because this is the formula for work. So don't worry about this, but know that kinetic energy is the energy of an object due to its motion. Okay, so this is how you derive a half mv squared. But don't worry about it, just know that kinetic energy is equal to a half mv squared. Then we were taught this concept in grade 10, we're returning to it. Okay, what is mechanical energy? So mechanical energy is the sum of an object's gravitational potential energy and its kinetic energy at a specific position. So every object has a certain amount of mechanical energy, and it's a combination of the potential energy and the kinetic energy. Then we have the law of conservation of mechanical energy. So in an isolated system where there are no external forces like friction or air resistance, the total mechanical energy of the system is conserved. So I like to think about this with this roller coaster picture. Can you see here? There's a blue potential energy bar and a green kinetic energy bar. And as the roller coaster gets to the top of a cliff, the potential energy bar is high and the kinetic energy bar is low. And then as it goes down the cliff, the potential energy decreases, watch, and the kinetic energy increases. And then as it goes up and down hills and loops the loop, the energy keeps being transferred between potential and kinetic. So this is the conservation of mechanical energy. The energy can't be created or destroyed, it gets transferred. And in mechanical energy, between potential and kinetic energy. So we use this in falling object situations. If we have a bowling ball on the top of a shelf, up here it's got potential energy, only potential energy because it's sitting still, and that's equal to mgh. There's no kinetic energy. If we let it drop, when it hits the ground here, its potential energy is going to be 0, but it will have a high velocity. All of the potential energy will have been converted to kinetic energy at the bottom of the fall. So this here is the definition you have to remember. The total mechanical energy in an isolated system remains constant. So the energy, the mechanical energy at A is equal to the mechanical energy at B. So look back here, A, B. So the potential energy plus the kinetic energy at A is equal to the potential energy plus the kinetic energy at B. Okay, so we know isolated systems, there's no net force acting on the system, so there's no air resistance or friction. So if it asks you what is an isolated system, a system is isolated when the next net external force acting on the system is 0. Pendulums are often important in this topic. So you know, a pendulum swings backwards and forwards like this. Okay, so at this point in its swing, the potential energy is at a maximum, and it actually comes to a brief halt up here, and there's no kinetic energy. But as it passes the bottom of the swing here, the potential energy is at the least and the kinetic energy is at the most, and then it comes back up here, all potential energy at its maximum and kinetic energy at its minimum. So the energy transfers, potential, kinetic, potential, kinetic, potential, kinetic, potential, like that. Because in an isolated system, the total mechanical energy is conserved. So this leads us as well to the work energy theorem. I think I should stop here. I think I've talked for too long.